This is Lecture 10G. It's an introduction to conic sections. I'm sure you've studied conic sections before in algebra and probably also in trig. For review, you have four conic sections: the circle, ellipse, parabola, and hyperbola. Along with these are degenerate conic sections. In the case of the ellipse and the circle, the degenerate conic section is a dot. That is when this circle, say, one geometric way to show these, that's what I'm showing here for the conic sections, is that you have some cone of light generated by some kind of light bulb right here, okay, right at that focus, at that vertex there, and it makes these cones of light. Then you take a piece of cardboard and you stick in through the light, and you notice what pattern's on there, and the pattern depends on the angle that you hold this cardboard with respect to the axis of these cones of light. And if you're directly perpendicular to the cones of light, this being the axis, let me draw the axis for you. So the axis would just go right down the middle of this, like that. Well, it's not exactly straight, but it would be straight down the middle of the cone of light. Right, if you're perpendicular to that axis, the pattern would be a circle. If you move the cardboard closer to the dot, to the source of the circle, it's going to be smaller. If you move it further away, it gets bigger and bigger and bigger, but it's still a circle. If you tilt it with respect to that axis, you start getting ellipses. The more you tilt it, the more elongated the ellipse. The flatter, closer to perpendicular you are, the more the ellipse is similar to that to a circle. It's closer to a circle. So you get a whole family of ellipses, and of course you can move this cardboard back and forth to get a smaller, larger, smaller size of these different ellipses. Now if you hold that piece of cardboard so the angle of the cardboard is exactly the same as the angle of the cone. So here's the angle of the cone, and if the angle of this cardboard is exactly the same as that, if it's parallel, you get a parabola. There's actually only one parabola per cone of light. You don't get all these different shapes like you do with a circle or ellipse. Now if you continue tilting past this parabola, past this situation for the parabola, then you get hyperbolas. If the cardboard does not hit the other cone, or like doesn't hit it for quite a while, you might not see the other branch of the hyperbola, but it will be there. Here, this shows a hyperbola, the two branches of the hyperbola, as the cardboard comes into the cone of light. It looks in this picture as though it is parallel to the axis of the cone. That is not necessarily, that's one hyperbola. There are many. As soon as you go beyond the angle for the parabola, you are then creating hyperbolas on your cardboard. The degenerate sections, conic sections, are the shapes that occur when this cardboard is, for the ellipse or the circle, when it's right here, right at the source of the cone of light, and then it will be a dot. For the parabola, you will end up with a line. If you took this parabola and ran it through the source, you would be right at that angle of the cones of light, and you would get a line. The degenerate parabola is a line. For the hyperbola, it is actually two lines. It's hard to show because of the way that they've positioned the cardboard here. So those are your conic sections. There's two basic ways in Cartesian coordinates to express these conic sections. One is in the so-called standard form, and that's the standard form of the equation. This equation will generate all the conic sections, depending on the values of, basically depending on the values of A and C. For example, if A is equal to C, the result will be a circle. If A is 0 or C is 0, the result is a parabola. The B term, the cross term with the coefficient B, if that is 0, then the conic section will either be parallel to the x-axis or parallel to the y-axis. If B is not 0, the conic section might be rotated. The chart shows other forms. The other form for writing the expressions for the conic section. This form is achieved from the standard form by completing the square appropriately. And this form is very graphing friendly in a sense. The H and K give the coordinates of the center for the circle, the ellipse, and the hyperbola. For the parabola, it gives the vertex of the parabola. So the h and k always being with y and h always being with x, that notation is very standard here. You have the equation for a circle, x minus h squared plus y minus k squared equals r squared. It's a circle of radius r with center at h and k. The ellipse is very similar. It's as you took the r squared, say you took the r squared and divided both sides of the equation by it, you would get equations similar to the ellipse, but a would be equal to b. But now if a is not equal to b, then you have an ellipse. Major axis parallel to the x-axis here. In this case, major axis parallel to the y-axis. And there's standard for switching the a's and b's around. Looking down at the hyperbola, very similar to that, to the equations for the ellipse. Oh, that was supposed to be a marker. Let me get rid of all that. So here's the equation for a circle. Divide both sides by r squared, and you would get this form with a equal b. If a is not equal b, you have an ellipse. Change that sign, that plus sign to a minus sign, and you have a hyperbola. Very small changes take you from one form to the other. The parabola is a little different from the others. It's written in this form because only either x is squared or y is squared. Now we're going to list here in this chart another property of these conic sections, and this property will lead us to the polar equations for the conic sections, which is the goal of this chapter. So for a circle, the eccentricity E is 0. It's perfectly round. Now note the progression here. I'm not defining E right now, but the eccentricity for an ellipse lies between 0 and 1. For a parabola, the eccentricity is 1, and for a hyperbola, the eccentricity is greater than 1. There are some expressions here for calculating the eccentricity for the ellipse and the hyperbola. The important thing here is just to see eccentricity is 0 for a circle, between 0 and 1 for an ellipse, 1 for a parabola, greater than 1 for a hyperbola. Now we introduce another concept that was usually used in algebra for the parabola only, and that's the idea of the directrix. For the parabola, the directrix was a line that sat outside of the parabola, and for a parabola, the distance from the focus, here from the focus to any point on the line, say this point, that distance, and then the distance from that point on the line to the directrix was equal. And that was the defining quality of a parabola. All of the conic sections also have a directrix, although it's not talked about a lot until you try to develop these polar equations. Right. Here's for the ellipse. There's a directrix here. It's located at a squared over c, a being the length of half the length of the major axis, and c the distance from the center out to the focus. And there's a similar property. I'll talk about it in a minute, but again, I'm going to take the distance from the focus up to some point P. I'm going to compare that to the distance from the point P back here to the directrix. For the hyperbola, similar situation. The directrix is at a squared over c again. It's lying between the two branches, and we're going to look at the distance from the focus up to that point P, and then the distance from point P back to the directrix. And from that, we're going to develop the polar form of the equations for the conic sections. So I've summarized the results about the eccentricity on this page. For the circle, eccentricity is 0. For an ellipse, it's between 0 and 1. For parabola, it is equal to 1. Hyperbola, eccentricity is greater than, well, there's an error. It's greater than 1. Okay. And what is the eccentricity? In general, it is the ratio of the distance from the focus to some point on the curve So we have the distance from the focus to some point on the curve, and we divide by the distance from that point over to the directrix, and that ratio is E.